Hello, I'm Steve Gallagher. I'm Head of Foam Control Technology at Hycontrol, and I'm going to introduce to you our foam control systems and the SureSense Plus controller. I've been working in foam control for 30 years and maybe more, developing systems and measurements for foam control in a whole range of different applications. And I'm going to talk to you today about foam and why it's important, and I'm going to talk about what we can do and how we can help you, how we can manage it, measure it, control it, and sometimes get rid of it. So why is foam of interest to us? Well, very often it's a problem. Sometimes it can be useful, but if it's a problem, it can be a big problem. At the simplest level, tanks of liquid can overflow where liquid turns into foam because of gas injection or stirring, and the foam can tip out the top, get on the floor, make a mess. It needs a lot of clearing up, it requires manpower, it can cause slip hazards and contamination problems. At the worst level, it can result in the damage to vessels in large anaerobic digesters. If foam becomes a problem, it can block up exit lines, it can destroy gas compressors, it can cause overpressure and the loss of the roof of a digester, which can cost millions of pounds to repair. In vacuum cooling applications where vacuum pumps are used to create vacuums, foam can get up the exit gas lines, get into vacuum pumps and cause destruction of the pump. In fermentation systems where sterility is very important, exit gas filters can get blocked by foam because of the liquid content, causing overpressure and complete loss of a process. So here are some pictures showing foam when it's out of control. Inevitably, if it's leaking out and spilling on the floor, which is a big problem, it can cause slips and injuries. People slide about, it gets in the way, it makes a mess. It might carry contaminants and present a biohazard in effect. It also means that we've lost the contents of a process because a liquid is turned into foam and has spilled out and been lost. We can't collect it up. It also means that the process has gone out of control. Something has gone wrong with the process control in many cases. So we characterize foam in two situations. One is open tanks where the foam can actually escape from the top and go onto the floor. There's nothing to stop it getting out. So it's ambient pressure. But we also have situations where we'll have a closed tank where there's a pressure and the foam can't get out in the normal way, but it could go out through a gas line or some kind of exit pipe and cause problems downstream. So first of all, if you want to control something, you need to be able to measure it. We want to be able to indicate that the foam is there, assess that the foam is there automatically, so someone hasn't got to stand and watch it. So why would we want to measure and control the foam? Well, first of all, we want to reduce waste and product loss through overfoaming, foam over situations. We also want to increase productivity and improve yields by making processes run better. In many cases, we'll add chemical antifoams or defoamers into a process in order to control the foam, and managing the quantity of expensive additions of chemicals is important. We don't want to have clean-up costs and manpower that's used up in tidying up things that have gone wrong. And we want to reduce waste. If a process goes wrong, the whole thing might have to be dumped. We want to improve process control and efficiency and prevent pollution. So these are all good reasons why we would want to measure and control foam, and we want to improve process control, we want to prevent damage, and we want to prevent loss. So what kind of situations might we see foam in? So there are lots of industrial situations, and there are a few pictures here. So pharmaceutical is one of our best markets. That's a situation where antibiotics and drugs of all sorts are made through biotech processes, and that often creates foam. Brewing and beverage, of course, everybody knows that you get foam on beer, and you want enough, but you don't want too much. Too much, a glass full of foam is really not much fun to drink. Food and dairy applications, vegetable processing, sugar manufacturing, all kinds of milk production creates foam. Wastewater, sewage works and industrial wastewater effluent treatment processes create foam, and you don't want too much of it. There are biotech applications for manufacturing all kinds of processes these days, all kinds of materials. So enzymes are created by fermentation processes very often. Yeast is created by fermentation, and there are many chemicals that are produced by fermentation routes. Sometimes chemicals produce foam. Vacuum cooling processes create foam where food is being cooled down quickly. Anaerobic digestion, which is becoming more and more prevalent in the UK and other countries, is a biotech process, a very specific one, and there is very often foam which can cause process disruption in digestion, and many environmental processes. And foam can be very varied. It can be very light, like the kind of washing up liquid foam that we see when we're washing dishes, to very dense foam in anaerobic digestion, which looks like you could walk on the top of it. It's not the same kind of thing as liquid, where it's the same all the way through. It varies. It's quite a complicated material, foam. We're used to it, so we think of it as being simple. We see it in our everyday lives, but it's actually very complex. So if we look at the composition of foam, foam is made mostly of gas, usually air, but it could be carbon dioxide or nitrogen or methane or some other gas. It's got a very small amount of liquid in it, which forms thin films around the bubbles of gas. Now, when we detect the foam, we only detect the liquid content, because the gas content in the bubbles is no different in most cases from the gas that's surrounding it. So we detect the liquid part of the foam, and actually there's not very much liquid in there, which makes it quite difficult to detect. It's quite a complex material, and it varies considerably, so the bubble size can make a big difference to the nature of the foam. Small bubbles means there's more liquid in there because there are more films of liquid, and large bubbles means there's less liquid. So depending on the size of the bubbles, you can have more or less liquid. So the very lightest foam has large bubbles with very little liquid in and is harder to detect. Interestingly, foam, as I said, is a complex material, so it's not the same all the way through. When you look at it, it looks like it's just foam, but actually it varies considerably. There are dynamic processes in foam. If we look at this diagram and if we think about what's going on here, we've got liquid at the bottom where bubbles are coming through and creating foam. The bubbles are coming up, floating on the top of the liquid and rising up. As the bubbles rise, so they start to drain and they get thinner and they break. So small bubbles turn into larger bubbles. So if we look at that and we look very closely, we can see that at the bottom of the column there are small bubbles of foam, and at the top of the column there are larger bubbles of foam. And the density of the foam varies from top to bottom. At the bottom we have small bubbles, at the top we have large bubbles, and it varies in between. So as the large bubbles are draining out and breaking and the water's running down through the foam, so at the bottom of the liquid surface, it's wet and dense foam. At the top of the liquid surface, it's drier foam, and the bubbles are larger, it's harder to detect. So depending on where we measure in the foam column, we actually can measure something a bit different. And we can measure something of the density of the foam by measuring the liquid content in the foam. So if we look at this as a section through the column and we consider the foam at the top of the column, it's drier than at the bottom, it's harder to detect. And as we go through the foam from the top to the bottom, we find that the density varies, the liquid content varies, and we go from a foam that's drier to a foam that's wetter. Now, this actually gives us some advantages in terms of measurement because we can use it to see what's going on in the foam. But it's also useful to bear in mind when we're trying to do measurements to know where we're measuring and what's going on. We can get foam and we can measure it, but then what do we do about it? How do we control it? And there are various ways to do that, but the commonest way is to add a chemical antifoam or a chemical defoamer into the process. Now what that does is it increases the drainage of the foam and the thin films become thinner and then the bubbles collapse and so the foam collapses. So by putting a relatively small amount of an anti-foaming chemical into the process, we can actually reduce the foam. So we add a chemical in, the drainage increases, the bubbles get thin and break and the foam collapses. And that's a very common way of doing it. It's not the only way, but it's a very common way of doing it. In lots of industries, traditionally antifoam is just added constantly. It might be added at a low rate, but it's added constantly whether it's really required or not. Because it can be difficult to predict in advance when foam is going to occur. So people just add antifoam as a constant part of the process. The problem with that is, of course, it's expensive. You're adding it whether you really need it or not. And there may be lots of times when you don't need it. And also it might have a bad effect on the process. So you might actually be reducing the efficiency of the process by doing that. In processes where we need good transfer of gas from the gas phase into the liquid, it can actually affect what we call the mass gas transfer. That is the transfer of gas from the bubbles into the liquid. By adding antifoam, it increases the bubble size in the liquid and that reduces the mass gas transfer, and in some cases it can reduce yield significantly. So in fermentation processes we're very careful not to add too much antifoam because it can actually cause more troubles than it solves. There are lots of different types of antifoam that we can use that are suitable for different situations, made of different materials. There are food grade versions, but again we don't want to add too much. A better way of doing it is to measure the foam. So if we measure foam, we detect when it's there and when it's not there, we can do something as a result of the foam being generated, and when there is no foam we don't have to do anything. And for all good control systems you want to have a good measurement. So in any kind of closed loop control you want to have a good measurement and assess what needs doing and then do it. So how would we go about controlling the foam in a typical situation? So this diagram shows a reactor in which we have some liquid and some foam. We have a stirrer that's stirring it up, and we have bubbles of gas, which either coming from the surface or perhaps we're introducing gas deliberately because we need that for the process. So the bubbles form on the top. I have a sensor or a probe that's in the foam, so we're using that to measure the foam and how it's increasing or reducing. And we might have a dosing pump in which we can add small amounts of chemical to reduce the foam, and the two are connected together by a controller. So we often have three elements. We'll have the probe, we'll have a controller, and we'll have a dosing pump. And we'll add antifoam when it's necessary, but only when it's necessary. And by doing that we can control the foam, we can stop it getting too high, or we can actually control it at a fixed level. And sometimes it's useful to do that. So here's a controller. This is a controller that we call SureSense Plus. our main device that we use for controlling foam, and we can connect a probe to it to actually create a foam control system. We've actually incorporated in this device the best effects, all the best features from our previous controllers. This particular controller can connect up to 3 sensors, so it's quite an advanced device. We can connect up to 3 sensors, and it has a number of outputs, and we can control up to 3 different processes at the same time, or we can do multiple measurements within one process. So this gives a great deal of flexibility in terms of control. So we could, for example, make 3 different measurements in one vessel. If the foam is very critical and we want to stop it coming out of the tank, or we want to stop it causing damage, we could, for example, have one probe with 3 measurement points, and the controller will measure all 3 of them and do different things depending on where the foam is in the vessel. So we could, for example, have one point that controls the dosing of antifoam. We could have a higher point. If the foam gets too high, we could have an alarm system. And yet a higher point, which is a panic alarm, which causes the process to shut down. I mean, in some cases, shutting down a process might be very useful if we're in danger of damaging equipment, like a gas compressor. Having 3 points in one vessel can be very useful. This controller has a series of menus. It has a display, so you can see what's going on all the time. You can see real-time measurements of the foam. You can see what the controller's doing in terms of having the effect on the process. And you can easily change it by using the keyboard on the front. It's got 5 different relay outputs that can be configured individually according to the customer's requirements. So we could use one for dosing, we could use one for an alarm, we could use one to control something else, we could use one to indicate that we're measuring liquid and not foam. So there's a variety of things that we can set up on the outputs. We also have a 4 to 20 milliamp output, which can be used to give you some indication of the level. And we could, as I said before, have 3 separate probes into one controller, thereby reducing the cost of an overall system. We can measure the liquid, so if we have a situation where the liquid control fails and liquid gets too high, so that a probe gets submerged in liquid, we don't want to at that point add antifoam into the process, so we can get it to detect liquid, give an alarm, shut down the antifoam control, or do something else. So it could be used for liquid level control as well. There are a variety of dosing algorithms that we've developed, so we can have a simple on-off device and something more advanced. I'll talk about that in a minute. We can actually use it to record how much antifoam we've added. If we enter the dose rate of the pump into the controller, we can actually use it to tell when the antifoam storage is running low, or get it to tell us how much antifoam we've used overnight, for example, when there's nobody in attendance. We can directly control pumps and valves, or some other kind of external controllers. We can signal to a PLC or a SCADA system. So here's a picture of a probe. This is a typical probe. Probes, or we might call them sensors, come in a whole variety of shapes and sizes. So this is a very common one. It's a 12mm diameter. It has no built-in particular fitting on it, so we can use it in a bracket or some kind of adjustable fitting that we can move. It's suitable for use up to 150 degrees centigrade, so it can be used in steam sterilizable processes. It also can be used for CIP, clean in place, where we're automatically cleaning processes down. It can take pressure up to 10 bar typically, although we can do high pressure as well. Hycontrol sensors come with a wide range of fittings. Every industry seems to have its own process entry system, its own process fittings. So we've worked with a very wide range of different fittings, and we have a range that we can offer. There's a wide selection, so we can make it longer, shorter. We also have a range of fittings which are adjustable, so we can offer you an adjustable fitting where a probe can fit inside, seal into a process and be adjusted in height to suit different applications that are happening in that same vessel. For larger applications and longer lengths, we use 20 millimeter diameter probes, which are more robust and will are heavier duty, if you like. The head on this is has a terminal blocks inside, and we also have a means in there to tell that the probe is wired up correctly. So if the probe is not wired or the cable is damaged, the controller can actually give an indication that something's gone wrong, which is a useful feature. The probes are also available for ATEX applications. They're certified for ATEX for hazardous areas where there are explosion risks, and we can supply them into those kind of applications. For example, anaerobic digesters are ATEX applications. Now, one of the problems with foam, apart from being difficult to measure, it also is sticky and creates a build-up and a sticky covering on probes. So after a while, the foam can dry out on the probe, or the product can splash onto the probe and leave a coating on the surface. Now, it's very important that the probe can still work with that kind of coating on it. You don't want a coating on the probe to be measured as if it's foam and have alarm events when there's no foam there. We have a technology that we call intelligent multi-action sensing, or IMA sensing, and this technology is used to distinguish between foam and fouling, or a build-up of material on the probe. So probes can work and continue to function even if they're coated in material. Here's a picture of a probe in a situation where it's covered in material and still working. This is a very small bioreactor, so that's the kind of serious fouling that can result from foam, and our probes can still work in that situation, and it's an important feature of foam measurement, that you don't want to measure foam when it's not there. Now here's how the IMA sensing works. When you have foam, as I said before, it's sticky, it can build up, it can dry out and stick on the surface. And in that situation, it can cause a short circuit on the probe to the side of the tank. And what we don't want is to be able to measure that as if it was foam. So we have a technology called IMA sensing, which is used to distinguish between the fouling and the foam. And it works by using two sensors. So we have one electrode in the probe which actually measures the foam, and we have another one which is mounted above it and is usually called a guard electrode, and that's used to measure the fouling. And by doing those two measurements, we can distinguish the foam from the build-up of material or fouling. So here's a bit more about how it works. The guard electrode mounted above the sensor electrode creates the effect of an isolation layer between the two. It creates the situation in which the sensor electrode will only measure foam which occurs below it, and the guard electrode will only measure the fouling which occurs above it. So by doing those two measurements, and by very carefully balancing the guard and the sense measurement, we can make the probe immune to a very high level of fouling. Of course, nothing works forever, and there comes a point when you have to clean probes. But with this technology, the maintenance is reduced to a minimum. Here's the screen of the controller. This is set up for one probe, which has 3 different measuring points. So the one probe is called P1, and the lowest measuring point is called S1. The next one is called S2, and the third one is called S3. And real-time measurements from those 3 points can be displayed on the screen. At the bottom of the display, we can see the function of the relays. So in this situation, relay 1 has been configured to dose antifoam. Relay 3 has been configured as an alarm. And along the top of the screen we can see the time and date. So we get real-time information about each of the probes or each of the measuring points on the screen at any one time. And that's quite useful, you can see what's going on. This controller is programmed through a simple menu system with a selection of levels in the menu and enables all these things to be changed and set up, configured according to the customer's requirements. Because there are quite a lot of things that can be set up, we've included a system of recipes. So in order to get you started, you could actually choose a recipe which is from a list of different applications. So you could choose a recipe for fermentation, you could choose a recipe for food production, you could choose a recipe for effluent treatment, and that will set up the controller and get you going. You could then change it if you want to and add things to it or change configurations or change sensitivities. One new feature in this controller is a Totalizer function. It can be used to accumulate how often the dosing pump or a valve or some other actuator is being run for. So if it's an Antifoam pump, it will add up the on time of the Antifoam pump, and you can enter in the dose rate of the pump, and so it will accumulate the added volume. So if you wanted to use that to tell you how much you had left in the tank, you could do that. So when you had a new IBC of Antifoam, you could zero that Totalizer, and over a period of time you can set an alarm to tell you, oh, it's almost empty and you need to change it at some point soon. There are 3 control algorithms that can be used in the SureSense Plus. The first one is simply on and off. So if you want to just do something when foam is being measured, you can select an on-off algorithm. So you might just choose to open a valve or have an alarm sounding when this foam is being measured. So you can choose an on-off algorithm and it will simply do something as long as foam is being measured. When the foam disperses, it will stop that output. Secondly, there's a shot and delay algorithm, which is a very common one that we've used for many years and is very commonly used for foam control. So basically it works by having an initial delay when the foam's first measured to be sure that foam is really there. And as long as foam's measured for a fixed period of time that can be adjusted, then it will do something. What it does is it will add a shot, so it will switch a relay on for a period of time that you can adjust, and that would add a certain amount of antifoam or have some other effect for a period of time, and then after that there's another delay. This allows something like an antifoam addition time to take action. Antifoam doesn't happen immediately, it takes a bit of time to get in and take effect. So by having a shot and delay, you can reduce the amount of antifoam, make sure you're not adding too much. And in fact, the best way to use antifoam is to put it in small amounts. So a small amount of antifoam added often is much more effective than a large amount added less often. And the third type of control algorithm, which is actually the most complex one, is a PI type control, which is similar to a PID without the D function. PID control means proportional plus integral plus derivative. Proportional control is where we measure the foam, compare it with a set point, which is the required measurement, to create an error, and the error drives the proportional part of the control. So the bigger the error, the bigger the proportional term. That's added to an integral. Integral is effectively a ramping up with time while there is an error there. So all the time that the error is there, the integral term will ramp up the proportional term to give a larger response. And we've included these two and added them together. The useful thing about this is it can control foam at a fixed level in a vessel. And in some processes that's very useful to do. It also means that it reduces the antifoam addition to the very minimum. So in effect, it can arrange for the antifoam addition to just balance out the creation of foam, and it will do that automatically. Now, to set this up, there are terms that you have to adjust. So there's a proportional factor and there's an integral factor. The proportional factor increases or reduces the effect of the proportional control or turn it off. The integral factor reduces or increases the integral term. And the two effects are added together. So with the PI control or adaptive control, we can arrange the dose rate or the addition of antifoam to just balance correctly the production of foam in the vessel. And this will have the effect of controlling the foam at a given level. It can also reduce the antifoam to the absolute minimum. The PI control is an advanced form of control, and it works by measuring the foam and comparing it to a set point. So we measure the foam as a percentage of the range. So the measurement can vary from 0 to 100%. And the set point is also 0 to 100%. So if we put a set point of 50% and the measurement of the foam is less than 50%, that's a negative error. And if we measure foam as it increases and it goes over 50%, that's a positive error. And we're attempting to get the foam to measurement to match the set point that we've put in. So if we want foam at 50% measurement, we'll adjust the foam by means of adding antifoam until the foam measurement matches the set point. When the foam measurement goes over the set point, it's because the foam's rising up higher. We'll then want to be able to do something, and we use the two terms in the PI control, proportional and integral, to effect it by means of the measurement of the error. So the error is the difference between the measurement and the set point. We're aiming at 50%. If the foam, for example, gets to 60%, it's 10% too high, the error is 10. So we use that error of 10 to drive or calculate the proportional and integral terms. So the proportional term is merely proportional in respect to the error. So if the error is 10%, the proportional term is 10% times the proportional factor. So if we set a proportional factor of 1, for example, then the proportional term will be 10%. And that 10% is then used to set the timing, the on time of the antifoam pump. And if the error gets larger, because the foam's rising up, then the on time of the pump will be longer and more antifoam will be dosed. So as the error gets larger, the proportional term will get larger, and that will increase the on time of the pump until there's more antifoam being added. That will cause the foam to subside, and the foam will drop down and come nearer to the set point. The set point, if you remember, is 50% that we're looking for. So as the foam drops down to 50%, the antifoam addition will get smaller. That's the proportional term. It's the simple proportion of the error. Bigger error, the more antifoam we add. The integral term, which is added to it, is slightly more complicated, and it's based on the error, but it's also based on time. So the integral term integrates the error over time. So effectively, every second it adds up the error. So if we have a 10% error, In the first second that will be 10%. In the second second that might be 20%. In the third second 30%, and so on. So the integral term gets larger as time goes on. All the time there's an error there. So in practice we would set an integral factor of less than 1, because otherwise it would ramp up too quickly. So as the integral term gets larger, that increases the on time of the pump as well. So we add these two terms together, the proportional plus the integral. The problem with the proportional term on its own is, as the error goes to 0, the proportional term goes to 0, and if we only use that, then the pump would turn off, and then the foam would build up again. But because the integral term is ramping up, and it ramps up as long as there's an error, when the error goes to 0, the ramp stops rising but stays where it is. So if we have a foam building up and it's coming above 50%, 55%, 60%, the error is increasing, a proportional term starts the pump running, the integral term will start to ramp up as well and run the pump even faster. As the foam comes down, subsides because of the antifoam, and the error comes down to 0, the proportional term will come to 0, the integral term will stay where it is, it will stay as high as it's reached. Keep the pump running slowly to balance out the effect of the new foam being created at the liquid surface. So we want to create an effect in which the integral term is just balancing out the effect of new foam by adding small amounts of antifoam just to stop the foam raising any higher, but we don't want it necessarily going any lower either. And if we do that and manage the foam at a fixed level, that actually reduces the antifoam addition to the very minimum. It's better than putting more antifoam in and dropping the foam down completely. It actually results in less antifoam addition, which means saved cost, which means better control. So those are the three algorithms. We have the on-off, the shot and delay, and the PI control. And you can choose whichever one is most useful for what you want to do. The shot and delay is effective. It's simple to understand. The PI control is more advanced, takes a bit more setting up, but gives you better control in the end, and you can choose. Another feature of the SureSense Plus that we haven't had before is what we call dosing jam, or a jam alarm. So this is the situation in which something might jam or stick or break. So if our antifoam pump jams up or stops working, or we run out of antifoam, or maybe the antifoam lines freeze up because it's cold weather, and so antifoam stop going in, we can use this feature to indicate that and tell what's going on. It could also be used for a valve or any other kind of actuation that we're doing. It could be used for pressure control. But the way it works is, if something doesn't happen within a set period of time, then an alarm's generated. And that something happening is the foam either going away or getting back under control. So if we're measuring foam and we expect to get it under control by a certain time, we could set 5 minutes, for example. If the foam is still out of control within 5 minutes, we can use the jam alarm to create an alarm, and it will tell us that something's gone wrong. The SureSense Plus has 5 configurable relay outputs, and they can be set up to do different things. Relay 1 is slightly different in that it's a changeover relay, so it can be used to switch something on or switch something off. Relay 2 to 5 are simply on-off type relays. They're not changeover relays, and they can be configured again to do a variety of different things. In addition to that, the first 3 relays are typically used for dosing type applications. So relays 1 to 3 can be used for dosing on 3 different points, and some of the alarms can be set up on there. Relays 4 and 5 can be used for a whole variety of different alarms, but they can't be used for dosing. So depending on the requirements, it's necessary in some cases to choose the right relay to do that job. The SureSense Plus also has a 4 to 20 milliamp output. This can be used to indicate foam, to retransmit the foam measurement to a PLC or some kind of process controller, and it responds to the measurement of the foam as the 0 to 100% range. So 4 milliamps would typically indicate there's no foam at all. 20 milliamps would indicate there's a lot of foam. As the foam rises up and the measurement gets larger, so the 4 to 20 milliamps increases from 4 milliamps to 20 milliamps. The 4 to 20 milliamp output can also be used to indicate an alarm. So if there's an alarm situation, you can configure the 4 milliamps to fall below 4, which is an alarm state, or increase above 20, which is also an alarm state. So it can be used to indicate an alarm if you only want to use the 4 to 20 milliamp output and not use the relays at all, for example. You can also segment the 4 to 20 milliamps. If you have a multi-point probe, the 4 to 20 milliamps can be used to indicate which of the probes is measuring by segmenting the 4 to 20 milliamp range into the number of measurements that you've got in the probe. So if we have 2 measurement points in the probe, we can have the 4 to 20 milliamp output indicating 4 to 12 milliamps for the lower sensor and 12 to 20 milliamps for the upper sensor. And it can also be segmented by 3 if we have a 3-point probe. There are a whole range of alarms that can be used and can be configured on a relay or on the 4 to 20 milliamp output. So by measuring the fouling using the guard electrode, we can indicate that the probe is reaching a point where it needs cleaning. So we could set an alarm which says, hey, you better get and clean your probe because it's getting covered too much in a layer of fouling. While the probes are low maintenance, there's always a point at which something needs cleaning. It may not be very often, but it will occur at some point. And this is a useful feature to indicate that something needs doing in terms of cleaning the probe. If the probe is measuring liquid rather than foam, we might want to know that. We might want to use it to control a liquid level. We might want to use it to indicate that the process has gone out of control or reached a certain point. And we can configure one of the alarms to indicate that one of the measurement points or any of the measurement points is measuring liquid. If the sensor becomes disconnected or the cable is damaged, we can set an alarm which will indicate that that's happened. Or maybe the sensor has never been wired correctly. So if the signal is not a meaningful signal, then the controller can indicate that by means of an alarm. And there are a number of other things that can be set. For example, you can have an output which indicates that dosing's happening. So there might be a good reason to do that, to signal back to a process controller that dosing's in progress. This diagram shows the connections of the SureSense Plus. The connections are configured in a series of separate terminal blocks which can be pulled out and wired outside the controller and then connected into the controller. On the left hand side we have the power input, and then there's an earth connection and a return connection. So every sensor does need a return connection, and there must be some way to connect a return path. Typically it's an earth connection. It could just be one mains earth that comes in, but each sensor could have a separate return coming back from each vessel, which is connected into the returns terminal block. And then there are 3 separate connections for each probe, and there are 3 separate probe connections, up to 9 altogether. So each probe has the sense connection, a guard connection, and what we call a test connection. The test connection is important because it's used to compensate for the length of cable. And we can have quite long cables. The cable length can be up to 100 meters. So the test is used to compensate for the cable length to make sure we have an accurate measurement. And we use multi-core cables for this. So we have a cable with 2 cores and a screen, and several of those inside one main cable assembly. So we connect one of the cores to the sense, another core to the test, and the screen of those 2 cores is connected to the guard. There's a terminal block for the 4 to 20 milliamps, which simply has a plus and a minus. There's also a screen connection for that that's connected to ground. There's an RS485 connection that's only used in the factory for setting up. This shows the cable that we use. This is a cable that will be used for a 3-point probe. So it's an unusual cable in that it has inner screens and outer screens. So it's like we have a cable which has got 3 separate cables inside it. It's a multi-pair cable. So we have the inner twisted pairs, which are the cores which are used for sense and test measurements. Each of those pairs has a screen which is used for the guard for that sensor, and then the 3 are together inside an outer screen, and that outer screen connection is connected to ground. That gives it immunity to interference and also acts as a return path. The new probes have 3 terminal blocks in the head if they're multi-point probes, or a single terminal block if they're a single point probe. It's very important that connections are made correctly. You may have tried foam control systems in the past and had some problems. Some people have the feeling that foam control probes don't work very well. But because of Hycontrol's IMA sensing technology and our very long experience of measurement and control of foam, and also that we've worked in a whole range of industries all across the world, our foam control systems have been developed and really do work. And they're designed to be reliable and in many cases fit and forget. So just lay aside for a moment your past experience of any foam control systems you may have had, and just be open to the idea that you don't have to live with foam like bad weather, but there might be something you can do about it. The SureSense Plus has been specifically designed to measure foam. It's been designed from scratch to measure foam. It's not, as some other companies do, a modified liquid level sensor or some other kind of modified sensor. It's been specifically designed for foam, so it's optimized to do foam measurement. And the SureSense Plus is the latest in Hycontrol's advanced control systems and includes all the best parts of previous designs and can be set up and configured easily to match a whole range of different applications and customer needs without the need for adding additional equipment. So that's introduction to Hycontrol's foam control systems and the SureSense Plus controller. So thanks for listening, and if you have any questions, please feel free to give us a call on 01527 406 800 or look at our website hycontrol.com or our specific website for foam control products, which is foamcontrol.co.uk. Thanks for listening. Bye now.